Hello, welcome to this next lecture in pattern recognition. We'll just briefly recall what has been done in the previous lecture. As I said, we consider pattern recognition as a two-step process: feature measurement extraction / classification. First, there are two steps. First, from the pattern, you measure some features. So each pattern gets converted to feature vector, and then there is the classification step. The classifier takes feature vectors and maps them to class labels. And as I said, this course is about mostly designing classifiers. Feature extraction is very much problem dependent, and hence there are not too many general techniques, but classifier design is what would mostly be concentrating on. And any classifier is something that maps feature vectors to class labels. As I said, function learning or the regression problem is a closely related problem to pattern recognition, and we will be considering both of them together. In both cases, the main information we have, as we seen last time, is a training set of examples. We are given a set of examples, patterns belonging to class 0 and patterns belonging to class 1, such as I got many A's and many B's, and I need to learn a classifier to distinguish A and B. So, the main information we have for the design is the training set of examples, and both for classifier learning as well as regression or function learning, we need to learn from the training set of examples. Okay. We have decided that we will be following the statistical approach to pattern recognition, so called statistical pattern recognition. The characterizing feature of it is that we model the variations of feature values through probability distributions. So, a feature vector belonging to a class now becomes a random variable, which takes different values with different probabilities. That is what is meant by variations in feature values is captured through probability distributions. So, each of the feature vectors, each of the features themselves will be continuous random variable, and the feature vector will be a vector of continuous random variables. As we seen, one immediate result of using the statistical viewpoint is that we can define optimal. Right? We looked at, for example, Bayes classifier, which says put the pattern in the class with highest posterior probability. Posterior probability, the probability that class is I given the feature vector, and we mentioned that the Bayes classifier is optimal in the sense that it minimizes probability of misclassification. In this lecture, we will show that the Bayes classifier is indeed optimal. Let us just briefly recall our notation. The script X denotes feature space, the space of all possible feature vectors. Usually, if you have n-dimensional feature vector, there is n features. Usually, the feature space is Rn, the n-dimensional real Euclidean space. Y is the set of class labels, will be some finite set. For most of the course, we will be considering binary classification, in which case y is 0, 1. X is the feature vector, it has n components, x1 to xn. I put a transpose on the expanded feature vector because all vectors are column vectors. Hence, a classifier is a function that maps the feature space to class labels. This is for every feature vector, there is a class label. For this class, our class labels are only 2, is a binary classification problem. So, class labels can be either 0 or 1. We also introduced the idea of class conditional densities and so on. So, to recall, F0 and F1 are the class conditional densities for class 0 and class 1. Both are densities over the feature space. Pi is the prior probability, the probability that y of x is equal to I. As I mentioned last time, y of x denotes the random variable denoting the class of the feature vector x. Similarly, Qi's are the posterior probability, that the probability that y of x is I conditioned on x. For a given x, what the probability that this class is I, those are the posterior probabilities. Still recalling our notation, as we mentioned last time, Bayes theorem is given there. We can get one conditional density in terms of the other conditional density. Applying to our current case, it tells you that Qix is Fix Pi by Z, where Fi is class conditional and Pi is the prior probability and Qis are the posterior probabilities, where the Z is the normalizing constant, which is simply F0 P0 plus F1 P1. So, now let us state Bayes classifier again. Bayes classifier is the function which given x assigns 0 if Q0x is greater than Q1x, otherwise assigns 1. As I said, Bayes classifier puts a feature vector x into the class whose posterior probability is higher. Q0 is the posterior for class 0. So, if Q0 is higher than Q1, I put x in class 0. So, that is the classifier. I put B a subscript and H to say is a base classifier. From our base theorem, we know that checking Q0 greater than Q1 is same as checking P0 F0 greater than P1 F1. So, all we need are class conditional densities and prior probabilities. And we are going to show that the base classifier minimizes probability of error in classification. Let us go through with the simple proof. As we know, each classifier H maps the feature space X to the set of class labels, that is 0, 1. So, for a given H, given a classifier, define Ri of H as the set of all X for which Hx is equal to I. That is, for example, R subscript 0 of H is the set of all feature vectors that get mapped onto class 0 by classifier H. So, R0 H is the set of feature vectors which will be put in class 0 by a classifier H. Similarly, R1 are the set of feature vectors that are put in class 1 by classifier H. As we defined last time, let f of H denote the probability of error for the classifier H. So, now we can derive an expression for f of H. When will we make an error? If the classifier says class 1 while it is actually class 0 or vice versa. So, f of H is the probability that X actually belongs to the region R1 H, where the classifier would say class 1, and also X belongs to class 0, or disjointly X belongs to R0 H and X belongs to C1. Because R1 and R0 are disjoint sets, these two events are disjoint and the probability gets added. Now, we can always write probability A and B as probability A given B into probability B. So, here I can write this as probability X belongs to R1 H conditioned on X belonging to C0 multiplied by probability X belongs to C0, and probability X belongs to C0 is the prior probability P0. So, now f of H becomes P0 times probability X belongs to R1 H condition on X belongs to C0 plus P1 times probability X belongs to R0 H condition X belongs to C1. Now, we know that condition on X belonging to C0, the random variable X has density F0. Similarly, condition on X belonging to C1, the random variable has density F1. So, I can write both these probabilities as integration of the corresponding density functions over appropriate regions. So, this becomes the value of Fh. Now, in this expression, there is something that is very important to note. R0H and R1H are mutually disjoint and they add up to the whole space, because given a H, every X is either put in the space R0 or put in the space R1. For all X in R1, the integral adds F0 into P0, and for every X in R0, the integral adds P1 into F1, which means for any classifier, the error integral is such that at every X, we either add a P0 F0 or P1 F. So, we actually integrate over the entire space either P0 F0 or P1 F1 at each X. At which X we put P0 F0 in the integral and at which X we put P1 F1 depends on whether that X is in the region R0 or R1. And all that the classifier can do is to change these regions. It can only decide at which points P0 F0 is counted in the integral and at which points P1 F1 is counted in the integral. The classifier can only change the regions R0 and R1. Okay. Now, let us look at what the base classifier's regions are. We know base classifier puts a pattern in R0 if P0 F0 is greater than P1 F1 and puts it in R1 if P1 F1 is greater than P0 F0. So, using the previous expression for the base classifier, the probability of error of the base classifier becomes integral of P0 F0 on R1 plus integral of P1 F1 on R0. But the R1 and R0 are such that in the region R1, P0 F0 is less than P1 F1 and in the region R0, P1 F1 is less than P0 F0, which means this integral is integral over the entire feature space of minimum between P0 F0 and P1 F1. Since for every classifier H, f of H is integral where at each X we have to put either P0 F0 or P1 F1 and both of them are positive quantities, and base classifier at each X picks the minimum of them. No classifier can do better than this. So, base classifier is optimal in the sense its probability of error is less than that of any other classifier. That is, given the knowledge of the probability densities, no other classifier can perform better. That is a very strong result. The classifier is very intuitive. If we put it in the class which has highest posterior probability, that automatically minimizes probability of error. So, one way of looking at this is, suppose the left curve is P0 F0 and right curve is P1 F1. So, essentially at any given x, this is a one dimensional feature space, though the x axis is the feature space. So, given any x, that is the value of P0 F0 there and that is the value of P1 F1, whichever is higher, I put it in that class. So, that line denotes the optimal base threshold. To the left of this line, they are put on this class, and right of that line they are put on that class, and the shaded regions are the error. The error comes from the area under this curve is the probability that a feature vector of this class will have value outside this line, and similarly area on this side is that a feature vector of this class will have its value on this side, right. So, as you can see, any classifier has to essentially put a threshold. Suppose I put a threshold somewhere else, one can see that the error integral is increased. That is exactly the proof that we have done. Okay. So, base classifier is of course optimal to minimize the probability of error, but how does one implement the base classifier? To implement the base classifier, we need the posterior probabilities. Those are not available to us. As I said, the only information we have is the training set of examples. Now, how do I get the posterior probabilities? As you already seen, it's enough if we have the class conditional densities and prior probabilities, because checking whether Q0 is greater than Q1 is same as checking whether P0 F0 is greater than P1 F1. Now, these class conditional densities and prior probabilities can be estimated from the training set of examples, and there are different techniques of estimating these class conditional densities, which we will consider later on in the course, and then one can implement the base classifier with the estimated quantities. One small caveat is that the base classifier is optimal if I exactly know the posterior probabilities, but if I am implementing the base classifier with estimated posterior probabilities, obviously the optimality no longer holds, because there may be errors in estimation, and hence my classifier is not truly the base classifier. But however it is, that is the best we can do. So, we will estimate the class conditional densities and prior probabilities from the training set of examples and implement the base classifier. We will of course look at the techniques for estimating and also many other details about base classifier as the course progresses. Okay. But base classifier minimizes probability of error. That is what we said. Our proof shows that it giving a class label which is wrong is minimum among all possible classifiers. But there are two kinds of errors in classification. You can classify a class 0 pattern as a class 1 pattern or a class 1 pattern as a class 0 pattern. These are variously called as false positives or false negatives, type 1 error or type 2 error, false alarm, misdetection and so on. Essentially, some of this terminology comes from Second World War. During the Second World War time is when this Bayes generation theory was actually developed, and the important classification problem to be solved is there are these radars to detect fighter aircraft, enemy aircraft. So, based on the radar signal reflection that we got, somebody has to make a decision whether what we have is a enemy aircraft coming in to bomb or there is no enemy aircraft. So, if those are class 0 and class 1, if I make an error, there can be two kinds of errors. One is when there is an enemy aircraft, I actually think there is no enemy aircraft, or when there is no enemy aircraft, just a flying bird or something, I may think that is an enemy aircraft. There are two kinds of errors, and obviously the cause of these errors are very different, right. A false alarm, that is thinking that something is an enemy aircraft, is only so much of inconvenience for people, because I may sound an alarm and everybody goes into bomb shelters. On the other hand, a misdetection, when there is actually an enemy aircraft, but I do not think that there is one, can be a very fatal error. Many people may die. Similar things happen in biometric recognitions. Suppose I have an identity authentication system. You give your fingerprint to authenticate a customer. If he is genuine customer, but the system says he is not genuine, it is only a phone call from an angry customer. On the other hand, a non-genuine customer gives his fingerprint and the system wrongly takes him to be genuine customer. That can be real loss to the system. So, in general, the cost of errors may be different, and we may want to trade one type of error with other. We may not be bothered about minimizing probability of error, but we may want to minimize the cost of error. Well, that can also be done. It is done by what is called loss functions. So, earlier we have been rating classifiers based on the probability of error, but a more general method to assign a rating or a figure of merit to a classifier is what is called a loss function. A loss function is a function whose domain is y cross y. Y, as you may remember, is the set of class labels. That is, given any pair of class labels, it assigns a positive real number. L is a function from y cross y to r plus is the positive real line. So, given any pair of class labels, it assigns a positive number to it. The idea is that on a given x, yx, the random variable, denotes the true class of x, h of x denotes the class label that a classifier h will give. So, L of hx comma yx denotes the loss suffered by a classifier h and pattern x. The classifier would call out h of x, whereas it should have called out y of x. So, the loss function measures the discrepancy between hx and yx, the cost of the discrepancy between hx and yx. So, the idea is that I choose a loss function, so that L of hx comma yx denotes in some units the actual loss suffered by h and a pattern x, in the sense that h would have called h of x, whereas it should have called y of x. Now, we can define our figure of merit f, which assigns a number to each classifier h as expected value of L of hx comma yx. This expectation is of course with respect to the underlying distributions of x, and such an expectation of the loss function is called the risk function. So, many classification algorithms actually choose a convenient loss function and then try to minimize the risk. Risk is the expectation of loss. So, let us take some examples. There is something called the 0 1 loss function, defined by L of a b is 0 if a equal to b, 1 otherwise. That is, L has two arguments, one is what the classifier says, other is what the true class is. If those are same, there is no cost, otherwise the cost is 1, irrespective of which error is made. So, it is like earlier thing. So, what will be the expectation of L? L is a 0 1 random variable. So, its expectation is same as probability that takes value 1, thus probability hx is not equal to yx, which is same as the probability of error we defined earlier. So, what we did earlier can also be done through loss functions, if we think of what is called a 0 1 loss function. But loss function can be more general. That is to say, even though loss on correct decision is 0, loss on incorrect decision need not have to be equal. In the 0 1 loss function, the loss on the incorrect decision is same. Whenever a is not equal to b, the loss is same. But we can in general have L of 0 1 not equal to L of 1 0. L of 0 1 is when I say 0 and true class is 1, versus when I say 1, whereas true class is 0. Now, the FH, which is the expectation of loss, which is the risk, is the expected cost of misclassification. Right? Essentially, the relative values of L 01 and L 10 determine how we can trade one kind of error with another kind of error. As it turns out, we will derive this later in the course. As it turns out, the base classifier in this case will be, it is once again based on the ratio of the posterior probabilities. Earlier, if the ratio is greater than 1, we are putting in class 0, but now if the ratio has to be greater than some threshold, which is given by L 01 by L 10. Just to intuitively get a feel for it, if L 01 is equal to L 10, that the two kinds of errors have the same cost, then is same as the old base classifier. On the other hand, suppose L 01 is 3 times L 10. What does that mean? L 01 is I say 0, whereas the true class is 1. So, wrongly classifying something into 0 is thrice as costly as wrongly classifying something into 1. That means, before I classify something into 0, I better be very, very careful, because wrongly calling 0 is 3 times as expensive. And hence, what does the base classifier say? If that be the case, is not enough if Q0 is greater than Q1. The posterior probability of 0 is greater than posterior probability of 1, that is not enough. Posterior probability of 0 should be 3 times, more than 3 times the posterior probability of 1 for me to take the risk and call class 0. So, that is essentially what the base classifier represents. We will show later on formally that this turns out to be the base classifier that minimizes risk. Okay. And once again, for the criteria of minimizing risk, base classifier is optimal. That also we will show later on. So, base classifier is indeed a very good classifier. It can minimize risk for any kind of loss function, and that's the best you can ask for. But its real problem is that it needs knowledge of class conditional densities and prior probabilities. If I know them, of course, I can do nothing better. But if I don't know them, they have to be estimated. The estimation has its problems. Firstly, it may be computationally very expensive, as you shall see. or it may not be feasible sometimes because the underlying densities are not very nice, or there might be other reasons why I may not want to estimate the classical densities. Of course, then I can't implement. Also, if I implement the Bayes classifier with estimated densities, because of the address in estimation, it may no longer be optimal. So, considering all this, implementation wise, I will go for Bayes classifier only if I have sufficient faith in the estimated classical densities. Otherwise, what do I do? Well, there are many other methods of obtaining classifiers. So, for the rest of this class, we will at least quickly review a few of them. Many of them will look at more details later on in the course. So, one other method which is very simple and often performs well is what is called a nearest neighbor classifier. What is the nearest neighbor classifier? We store the training example, the feature vectors from the training set as prototypes. We can choose some of them or we can choose the whole training set, but anyway, we take the training examples, store them and call them prototypes. The thing to remember is that because the training set for each prototype, we know the actual class label because we have the training set. Now, we are ready to classify. Given a new pattern, we find the prototype x prime that is closest to the new pattern x and then classify x into the same class as x prime. That is, now you give me a new pattern x to classify. Within my prototypes, I search for x prime that is closest to x. Now, because x prime is a prototype, I know the class label of x prime. I give the same class label to x. The idea is if I have sufficiently many prototypes, anyone lying close to a particular prototype should have the same class label as the prototype. Okay. A slight variation is what is called a k nearest neighbor rule. So, instead of finding one closest prototype, I may find 5 closest prototypes and then take a majority rule. In a 2 class case, if I find 5 closest prototypes, 3 or more of them are in one class. So, I choose that class for x. It's kind of if a pattern happens to be near the class boundary, instead of taking one nearest prototype, taking a few more and taking the majority decision generally gives you lesser errors. This is called a k nearest neighbor rule. Generally, you take k to be the k to be an odd integer, small odd integer, 3 or 5 or 7. Okay. There are two main issues in designing a nearest neighbor classifier. We have to decide what we want to choose as prototypes. Do we want to choose the whole of the training set as prototypes, or if we want to choose a subset, which subset should we choose? And what do you mean by closest, right? What distance is the most appropriate distance? But given that we can solve these two issues, this is a very simple classifier to design and operate. Really, there is nothing I need to do except to store the prototypes. And the classification rule is also very simple. I just need to find a prototype that is closest to the new pattern and classify it into the same class. The actual performance, how much of time and memory you need, depends on the number of prototypes, how complex is the distance function and so on. Selection of prototypes. How do I select? How many to select? There are a few techniques. We may come back and discuss it a little while later. Essentially, we like to make sure that there are enough prototypes at all parts of the feature space. So, that wherever I get a new pattern, I have some prototype that is closest and of the same class to the new pattern. What about the distance function? One can of course choose the Euclidean distance, because all our feature vectors are real vectors. So, I can use Euclidean distance as the distance. The only problem with Euclidean distance is it's very sensitive to actual numerical range. If different features take values in different ranges, the ones which are numerically higher will dominate. Suppose there are two features, one feature takes values between 100 and 200, another feature takes values between 0.1 and 0.2. No matter how much you differ on the 0.1 and 0.2 feature, the first feature always dominates. So, we can always normalize with respect to variation of individual feature values. So, I can choose a distance function where the ith term in the Euclidean distance is weighted by 1 by sigma I, where sigma I is the estimated variance of the ith feature. Given all the examples, I can find the estimated variance of the ith feature and I can use that, so that I understand a difference between xi and xi prime relative to its standard deviation. A slightly better thing is to actually make this distance dependent not only just variances of individual features by the entire covariance matrix. So, I can make the distance function as x minus x transpose x prime transpose sigma inverse x minus x prime, where sigma is the estimated covariance matrix, and this is called the Mahalanobis distance, often used in economics. Okay. We will come back to this later on. What can we say about the nearest neighbor classifier? How does it perform? It of course uses no statistical information. It is a very simple intuitive classifier, but one can show that asymptotically, that is, as the number of examples, that the number of prototypes approaches infinity, if we assume that the prototypes are independently drawn, then the error made by nearest neighbor rule is never more than twice that of the base error. That is, the probability of error by base error is 0.1, then nearest neighbor rule never makes more than 0.2 probability of error. That is, if base rule can be 90% correct, nearest neighbor rule is guaranteed to be at least 80% correct. This is quite interesting, because instead of doing all the costly estimation implementing the base classifier, I can simply implement the nearest neighbor classifier. If with the given feature vectors, my base rule can give me very good performance. Let us say error by the base classifier is only 5%. Then at worst, my nearest neighbor may give me 10% error, which might be tolerable. But suppose the pattern recognition problem is very complicated, and base rule can give you only 80% accuracy, then unfortunately nearest neighbor may give you as little as 60% accuracy. But that apart, this is a very interesting issue, that even though we do not use much statistical information, we can still bound the error of the nearest neighbor by twice that of base error. It is also related to certain what are called non-parametric methods of estimating class conditional densities. We will discuss that later. But at this point, I will simply mention that because of its simplicity and because of its some guarantees and performance, nearest neighbor classifier is often the benchmark for any classified design. That is, I should not go for a complicated classifier unless I am at least getting sufficient improvement on nearest neighbor classifier. So, given any problem on the chosen feature vector, I should first implement the nearest neighbor classifier. That tells me the minimum performance I can get without doing any work. So, if I am designing a complicated involved classifier, there should be some reason. So, nearest neighbor performance by the nearest neighbor classifier is often used as a benchmark to say whether my specially designed classifier is doing well or not. Okay. Well, base and nearest neighbor classifiers are not the only classifiers. There are many other approaches to classified design. Okay. We will consider another approach in this introductory class, which is called the discriminant function based approach. So, the structure of this classifier is the following. As you know, a classifier is a function that maps every feature vector to 1 or 0. We are only considering two class case here. So, I choose a classifier structure as h of x is 1 if some other function g of x is greater than 0, 0 otherwise. That function g is called a discriminant function. Of course, I have to design the discriminant function, and a classifier that uses this structure is called a discriminant function based classifier. Because if I choose g of x to be q1x minus q0x, then this is the base classifier. If q1x minus q0x is greater than 0, then I put in class 1, otherwise I put in class 0. So, that is same as base classifier. So, base classifier is also a discriminant function based classifier, where the discriminant function is obtained using the posterior probability. But the interesting thing about discriminant function classifier is I can choose any other discriminant function too, right. The idea is I will try to tweak a proper discriminant function instead of worrying about actually estimating the class conditional densities. Okay. So, the idea is instead of assuming some functional form for the class conditional densities and estimating them, we can assume a functional form for G and directly learn the needed classifier. Okay. Generally, a discriminant function would be specified by some parameters so that I can tweak the discriminant function. So, let us say g w comma x instead of g of x is the discriminant function, where w is the parameter vector, and let us say there are capital N number of parameters. Okay. So, here is one example discriminant function. I can take the number of parameters of the discriminant function to be 1 more than the dimension of the feature vector, and the discriminant function is simply wi summation I is equal to 1 to n wxi plus w naught. That is, I weigh each feature component with some weight wi and then add a threshold, and if this sum is greater than 0, I put in one class, less than 0, I put in the other class. Okay. Where w0 to wn are the parameters, x1 to xn are the features, right. Such a function, such a classifier is called a linear discriminant function based classifier. This is linear because it is linear in the components of the feature vector, okay, or in the parameters. Linear discriminant functions are another important class of classifiers. Okay. So, let us just go a little bit deeper into it. A linear discriminant function based classifier, as we have just seen in the previous slide, is given by this. Very often we may not want, see this extra constant term may look as if this is not really a linear function, but we can easily get rid of the extra constant term. We take a new feature vector which is same as the old feature vector x1, x2, xn, but it has one extra component which is permanently set to 1. Okay. Take this as the new feature vector, it is often called the augmented feature vector. If w0 to wn is the parameter vector, then my classifier is nothing but I take, then I can write this w0 is w0 into 1, which is same as w0 into x0. So, the entire thing is now simply a dot product between two vectors. So, I find w transpose x, and the sign of the w transpose x is what determines the classification. This kind of a classifier is one of the earliest classifiers designed in 1950s. It's called a perceptron. We will come back to perceptron later on, and we will also find out how one fixes w or how one learns w from the training examples. In considering linear discriminant functions, there is one concept that is very important. Given a training set xi yi, so that is set of patterns xi along with class labels yi, we say this training set is linearly separable if there exists some w star such that xi transpose w star is greater than 0 if yi is 1, that is xi comes from class 1, less than 0 if xi comes from class 0. Of course, the labels 0 and 1 are arbitrary, which I call class 0 and which I call class 1 is arbitrary. So, essentially if there exists a w, so that xi transpose w star greater than 0 means is one class, less than 0 means is another class. Okay. If such a w star exists, then we call the set a linearly separable set. Okay. Any w star that satisfies this is called a separating hyperplane, and it is easy to see if there exists one separating hyperplane, there exists infinitely many. What does this mean? In geometrically, a w can be, so let us look at a figure. So, basically what we have is a line, often the line passes through origin, even otherwise it is alright. So, w transpose xi plus a threshold greater than 0 one class, less than 0 another class simply means that in the feature space between the two classes I can put a line such that all patterns of one class are on one side of the line, all patterns of the other class are on the other side of the line, right. That is what this means. Recall that x is an augmented feature vector, right. So, essentially x transpose w is given by w xi plus w naught. So, that is the line, and as you can see, if there is one line that can separate the two types of patterns of the two classes, then I can draw many other lines. There will be actually, as a matter of fact, a whole cone of lines, and any line passing through this cone would be a separating hyperplane, right. So, whenever a training set is linearly separable, if there exists infinitely many separating hyperplanes. Okay. So, a linear discriminant function will certainly work if the training set or let us say the pattern classes themselves are linearly separable. Okay. Now, how do I learn linear discriminant functions? We need to learn the optimal w from the training samples. Perceptron learning algorithm is one of the earliest algorithms for learning linear discriminant functions. It finds a separating hyperplane if the training set is linearly separable. Because the sad thing about this algorithm is that if the given set is not linearly separable, the algorithm cannot come out and say it is not linearly separable, it will just go into an infinite loop. So, if I know if I suspect or have good confidence that the training set is linearly separable, then perceptron is a very good algorithm to use. We will study perceptron algorithm, its convergence proof, and many other interesting aspects of perceptron algorithm later on. But in general, when we may or may not know whether training set is linearly separable, we can also use the disk minimization approach to learning linear discriminant functions. How do I, what do we mean by use disk minimization approach? Just like what we did in the risk minimizing based classifier, you choose a convenient loss function and then define expectation of the loss function as risk, and find a linear discriminant function that minimizes the risk, right. So, let us look at a little more into this. So, the idea is I want to minimize some criterion function. So, to minimize, what is the criterion function? The criterion function should evaluate different choices of discriminant functions, and each choice of discriminant function is choice of a particular parameter vector W. So, ultimately I am asking, can I write a criterion function that can evaluate different W? We can always use the old function. If I am using a linear discriminant function with W as the parameter vector, let us say h of W comma x as we given earlier is the classifier. So, L of h of W comma x comma yx is the loss suffered on h on a pattern x if it uses parameter vector W. So, I take its expectation and that is the risk for W. So, now what you want to do is to find a W that minimizes this expectation. Now, how do I minimize the f? Given a particular W, if I want to calculate f of W, I need to evaluate this expectation, and to evaluate this expectation we need the underlying probability distributions. Now, if I have the underlying probability distributions, of course, I can use the Bayes classifier. So, what do I do? How do I evaluate this f? The idea is that here f is expectation of some function, and as you know, if you want to find mean of some random variable, a good approximation is the sample mean. So, if I have training examples, I can find the sample mean of the same function on the training examples, and that I can use as an approximation to approximation to risk f W. So, let us call such a function f hat of W. So, f hat of W is L of h W comma x I comma y I summed over 1 to L and divided by 1 by L. As you can see, f is expectation of this L of x, so to say. So, if I want sample mean, it is L of x I summed over I divided by the number of samples. That is what f hat is, right. I sum the loss over the samples x I y I and divide over the number of samples. So, the sample mean estimated for f hat. So, we would expect that f hat is a good approximation to f. Why? Law of large numbers, right. We know if there are sufficiently many samples and samples are independent, then sample mean is a good approximation to the population mean. Sample mean, as a matter of fact, converges to the true expected value, that is the law of large numbers. So, f hat is a good approximation to f. Okay. So, we can minimize f hat instead of minimizing f, because f hat can be calculated. Given the training set, I can calculate f hat. So, let us understand this again. F hat measures the error of classifier on the training samples only, because it is obtained as a sample mean. F, of course, is obtained as an expectation. So, it measures error on the full population. So, what we are saying is that why do we use f hat? We cannot calculate f because we may not know the underlying probability distributions. So, we are calculating f hat, which can be calculated. So, our gut feeling is that if there are sufficiently many representative training samples, if the sample is large and they are independent, then the sample mean should be a good approximation to population mean. So, f hat would be a good approximation to f, and hence minimizing f hat should be good enough. Because there are a few deeper issues involved here, issues that concern what is called statistical learning theory. We will deal with that later on. Okay. So, this is what we want to minimize to learn my linear discriminant function. How do I minimize this? There is still a problem. We can have special algorithms such as perceptron algorithm, which can find a W that such that f hat W is 0. That would of course be minimum, because we know loss function values are all positive. So, for any given W, f hat W is always greater than or equal to 0. So, if I can find one W for which f hat W is 0, then that is the minimum. So, there can be some special algorithms which try to find that. But in general, we have to use a standard optimization technique, standard or otherwise some optimization technique. Now, can we always use an optimization technique? There is still a problem. This is f hat, and let us recall that the classifier h is the sign of W transpose x. If W transpose x is greater than 0, is one class, less than 0 another class, which means h is a discontinuous function, right. And we still haven't decided what loss function to use, but if you use 0 1 loss function, then loss function is also discontinuous. Now, irrespective of that loss function is discontinuous or not, if h is discontinuous, then f hat is discontinuous. If L is discontinuous, f hat is discontinuous, which means we cannot use any standard optimization algorithms for minimizing this, because we cannot even differentiate f hat. Well, we can get around this problem by changing both our H and L so that they become differentiable. We redefine H so that instead of it taking values 0 and 1 only, we see H takes values in the interval 0, 1. So, for example, earlier we said H of W x is the sine of W transpose x. Now, instead of saying sine of W transpose x, we say H W x is 1 by 1 plus exponential minus W transpose x. How does this function look? If I plot W transpose x on the x axis, 1 by 1 plus exponential minus W transpose x has this kind of form. As you can see, if W transpose x is a little positive, it is close to 1. If it is a little negative, it is close to 0. But the nice thing is, it is nicely differentiable. As a matter of fact, in the definition of the function, we can add a small parameter inside the exponent, and based on the value of that parameter, I can make this function as steep as I want. So, this is kind of a continuous approximation of the step function, that is the sine function. Now, when I use this H, if the output of H is greater than 0.5, I can put in this class, less than 0.5, I can put in this class. So, by changing H from sine of W transpose x to this, we have made H differentiable. Such a H is called a sigmoid function. Okay. So, we solve one problem, namely non-differentiability of H. We can similarly solve the non-differentiability of L by, instead of taking a 0, 1 loss function, we can take a squared error loss function. So, we take LAB to be A minus B, which is called the squared error loss function, which is also very popular in pattern recognition. So, now f hat W will be 1 by L summation H of W comma xi minus y of xi whole square. So, this now, because H is differentiable and the square function is differentiable, one can differentiate. So, for example, one can use gradient descent to optimize this, right, and such an algorithm is called the LMS algorithm. Okay. We'll look at LMS algorithm later on. So, there are efficient algorithms for learning linear discriminant functions. We will be discussing some of these techniques for learning linear discriminant functions later in the course. Okay. So, essentially we considered 3 approaches so far: the Bayes classifier, the nearest neighbor classifier, the linear discriminant function based classifier. Okay. Well, there are a few more, but let us just look at a summary of where the linear discriminant function based classifiers can take us. There are efficient algorithms for learning linear discriminant functions, okay, and essentially a discriminant function based classifier is more general, right. We just said it depends on discriminant function. So, we can also use nonlinear discriminant functions. The idea of minimizing f hat using a square error loss function works even for nonlinear discriminant functions. Okay. Now, but nonlinear is not so straightforward. Okay. The method we got of minimizing f hat W to find linear discriminant function is a generally efficient method. So, in general, learning linear models is efficient. Okay. But a linear discriminant function may not always be sufficient. Linear separability may be restrictive condition. Even if I minimize the risk of the best linear classifier may still be a poor fit. Right. Now, if I want to learn nonlinear discriminant functions, how do I go about it? In this course or even in the field, there are a few general approaches to learning nonlinear classifiers. Okay. So, I will briefly tell you 3 approaches for learning nonlinear classifiers, each of them to be viewed as a stylized way. This is still an interactive lecture. So, we are just surveying the field. So, at this level of detail, I will just give you 3 possible viewpoints on how one tackles nonlinear functions, nonlinear discriminant functions. One is what can be called a neural network idea. See, a linear discriminant function, I know how to parameterize W transpose x plus W naught. So, in a similar way, I have to find a good parameterizer class of nonlinear discriminant functions. Okay. One good class of such nonlinear discriminant functions is what goes under the name multi-layer feed forward neural networks. The basic idea is the following. Each of these circles here are essentially linear discriminant functions. So, I give my give the pattern to many linear discriminant functions, and I keep taking the outputs of the linear discriminant functions and combine them through linear discriminant functions. So, it is a kind of function composition approach to finding nonlinear functions. Okay. This using nonlinear functions are built up through composition of simple linear functions on those sigmoid functions that we talked about. Multi-layer feed-forward networks are a particular class like that, and is useful for learning nonlinear classifiers, and in this course we will be considering this as one approach to nonlinear classification. And another idea is, if a linear discriminant function does not work in the entire space, I can ask, can I cut the feature space into different regions, so that within each region a linear classifier would work. Here is an example, right. So, the shaded region is one class, the other region is another class. So, a single line cannot separate one class from other, but if I can put two lines, so that for example, in one half of the feature space I can use one line, in the other half of the feature space I can use the other line. So, one way of doing this is that I first cut the feature space with respect to one line. Let us say I cut it with respect to a line like that. That is what I call H1. Then I am asking that the feature vector fall in this side or that side. Depending on which side it falls, I can once again say I can use two different linear discriminant functions to classify. So, instead of classifying the pattern in one step, I will use multiple linear discriminant functions, right. This is like cutting the feature space into different regions, and within each region using a linear discriminant function. Such tree based models are possible for both classification as well as functional learning. Right. Time permitting, towards the end of this course, we will look at a few ways of learning such tree based classifiers. What is the third approach? A third approach is what may be called an SVM approach, which SVM stands for support vector machines. This is today possibly the best way to learn nonlinear classifiers. The idea is very simple. You map X, the feature vector, nonlinearly into a high dimensional space, and then learn a linear discriminant function there. What does that mean? Suppose the feature vector has two components, x1, x2. Suppose there is a function phi that maps R2 to R5, given by Z is phi of x is now a, I am sorry, it should have been 6, is a 6 component vector given by 1, x1, x2, x1 square, x2 square, x1, x2. Now, if I think of a linear discriminant function, a0 plus a1 x1 plus, think of a nonlinear discriminant function, a0 plus a1 x1 plus a2 x2 plus a3 x1 square plus a4 x2 square plus a5 x1 x2, that is a linear discriminant function in the Z space. Right? In terms of components of Z, this is linear. Right? What does that mean? Say, for example, in the original feature space, xy space, everything inside the circle is one class, outside the circle is another class. Now, this is essentially non-linear, because no linear function in x can separate the two classes. But if I change my axis, so that I have x1 square, x2 square, x1, x2 as my axis, then in the new space, all the points inside the circle will come on one side, all the points outside the circle come on the other side, and a hyperplane can separate them. Right? So, this is the basic idea of SVM. You map x non-linearly into high dimensional space and try a linear discriminant function there. Right? That is the basic SVM idea. Right? So, these are the three ideas that we use to learn nonlinear classifiers. Right? So, let us summarize our discussion so far. The Bayes classifier minimizes risk under any general loss function. Given the knowledge of class conditional densities, no other classifier can do better than this. We have seen the optimality of Bayes classifier in the simple case of minimizing probability of error. We will also prove it under minimizing general disk function. But any case, Bayes classifier minimizes risk under any general loss function. Its main problem is that it needs the knowledge of class conditional densities. How do I get class conditional densities to implement Bayes classifier? I can estimate the class conditional densities from the training set of examples. I there are various estimation techniques. We will look at each of them in this course and see how we can estimate the classical densities, what are the errors in estimation and so on. Okay. That is one kind of approaches to classifier design. But as we said, there are approaches other than the Bayes classifier. Nearest neighbor classifier is another approach to classifier design. Nearest neighbor classifier is very simple. It simply says find a prototype that is closest to the given pattern and put the pattern in the same class as the nearest neighbor. A variant is KNN. Instead of finding one closest neighbor, you find k closest neighbors and put the classifier in the in the class of the majority class. So, either nearest neighbor or KNN is a very simple classifier to implement, and as we have seen, it has surprisingly effective classifier. In many situations, nearest neighbor classifier gives you sufficient performance and you do not need to go for any more advanced classifiers. And in any case, even on a more complicated problem, a nearest neighbor classifier is always implemented because that gives you some baseline performance that you can always rely on, right. So, nearest neighbor classifiers is one other approach, and the issues there are how do I choose the prototypes, how do I decide on the distance metric and so on. Okay. But given certain choices for these issues, a nearest neighbor method is a simple and very effective classifier. When we consider certain techniques for density estimation, we will come back to the nearest neighbor classifier, explore its relationship with Bayes classifier and revisit the issue of how to bound the probability of the nearest neighbor classifier by the Bayes classifier error. Okay. Another method for classifier design is based on what are called discriminant functions. Okay. What does the discriminant function Bayes classifier do? It uses a function g, and the classifier simply says h of x is 1 if g of x is greater than 0, it's 0 otherwise, and such a g is called a discriminant function, and g may have a parameter vector. And now learning a classifier is essentially learning the parameter vector of the discriminant function. We have seen one example, namely linear discriminant functions, as one example of discriminant functions. Okay. I have also said that we can use the same risk minimization approach with which we have shown the optimality of Bayes classifier for learning linear discriminant functions also. Okay. So, even though to use risk minimization approach, we may not be able to use 0 1 loss function, we have to use squared error loss function. Learning discriminant functions using squared error loss function and minimizing the risk is a very standard approach to learning linear models. Okay. That is why many linear learning linear models go under linear least squares learning approaches. So, both for learning classifiers as well as regression functions, we often use a linear model, use a squared error loss function and minimize risk. Of course, we cannot calculate risk, as I said, because we do not have the underlying probability distributions, but we can always approximate the expectation by the sample mean and hence obtain the f hat function, which is often called the empirical risk function, which is nothing but the sample mean of the expectation. And because the sample mean can be evaluated on the samples, we can always minimize the sample mean. So, minimizing square error is one method of learning linear models. We'll discuss some methods of learning linear models. Specifically, we look at perceptron algorithm, we look at LMS algorithm, we look at what is called logistic regression and so on. So, we will discuss some methods for learning linear models. Okay. What is also good to know at this point is that learning many of the nonlinear models can also utilize the same approach, risk minimization approach. That is, we choose a suitable loss function, very often square error loss function, and minimize the f hat function, that is the empirical risk, to find the best parameter vector. Okay. So, both for learning linear models and also for learning some of the nonlinear models, we will often use minimizing risk using a suitable risk function. As we said, linear classifiers may not be able to deliver the performance needed, and we have seen at least 3 approaches. We will certainly explore both the neural networks and SVM approach for learning nonlinear classifiers. Both of them have some specialized algorithms as well as risk minimization algorithms. So, we look at them also as risk minimization methods. Okay. So, this kind of completes the overview of the course. Okay. From next lecture, we will start again at the Bayes classifier and go into the details of design of Bayes classifier. Thank you.